Welcome guys. It is Tuesday morning. Welcome. First of all, let me plug in my microphone and let's check if my voice is clear. Can you hear me? Okay. I need to visit internet, Safari. Okay. Okay. It's freezing. Okay. Can you can you hear me? Mhm. Okay. Can you can you hear me? External microphone. Let's see. Can you hear? Can you hear me now? Can you hear me? Guys, hello. Hello. External microphone. Let's see. Can you hear? Can you hear me now? Oh, I see. There is a noise. There is a noise. I have another problem. There is a noise. You don't like that noise. You don't need that noise. What we can do? What we can do instead? Let's just use our microphone. Let's just use the default microphone. Another problem. It's a noise. You don't like that noise. You don't need that noise. What we can do instead? Let's just use our microphone. Let's just use the default microphone. This is better, alright? This is better, right? Another problem. Okay. Nice. That's good. That's fine. That's fine. Stream. We are ready to go. Yes, we are ready to go. Let's go. Let's complete this series of videos, series of videos to make our own computer. That's my light. Wow. Okay. I fixed this one, CR ledge and D ledge. This was not difficult, but this one was difficult, you know. Because in here, it was so simple that I couldn't fix it. I couldn't solve it. So here, I asked for help, and it says you need to use some kind of circular connection. And I was thinking maybe I need to use this one and do circular connection, or use this one and do circular connection. But it turns out I just need two NAND components. Okay. So after this, next component was d-latch. So d-latch, it holds also it also holds a bit, a single bit, but it depends on this st value. Look, like if it is 1 and d is 1, output should be 1. If it is 0, s is 0, but d is 1 or 0, it doesn't matter, it should return the previous value. If it is 1 and 0, it should return 0. So it is another version of CR latch. So in CR latch, it was like we also had the two inputs, two flags, and it was like this one was not activated anyway. We only used these 3 points, three conditions. This was never used. So we did this one, and now we need to fix, we need to solve this one, and this one, and in the end, it's RAM. Okay, let's go. Using latches, you can build a circuit that changes its state over time, but a problem appears then, since state changes are not synchronized across the circuit, changes ripple through the circuit in an unpredictable order, leading to race conditions and generally unpredictable results. The solution is clock signal, one bit signal which periodically changes and which is connected to all stateful components. If components only change output when the clock signal changes, then changes will happen across the circuit at the same time, and we will avoid synchronization issues. In this task, you will build flip-flop component that stores a bit when clock signal is 1, but only starts emitting this. Okay, in this task, you will be building flip-flop component that store a bit. Okay, it stores a bit only when clock signal is 1, but only start emitting a stored bit when the clock signal changes to 0. Aha. If clock is 0, if clock is 1, get and store it, okay? If it is 0, emit, send, okay? What I did here. Okay. What we can use? Let's think. Look. If if st is 1, d is 0, output is 0. Fine. If it is 1, 1, output is 1. Okay, fine. 0, 0, 0, 0, 1, 0. Okay, now we need to build another version of data latch, here. For example, here, it stores a bit also, but it emits at the same time. When st is 0, the last stored bit is emitted, and the current value of d is ignored. I don't think this works. Delete. Let's just use this d latch, okay? D latch, and it says that we depend on this clock, right? If this is 1, then store the value, okay? Store what? Store the D value, right? So input flags and it can change in this stage. Oh, I see. So here, when it is 0, if when the clock is 1, the stored value is not yet output. The stored value should not go out, should not be output. We can use this guy. Why? Because we can say it also has a flag, a C flag, a S flag. When clock is 1, look, when clock is 1, let's do the D1, okay? When the clock is 0, what should we do? I think the logic should be like this, similar to this thing. When it is 1, we should not output anything, When it is 0, we should output, right? Let's check it. Set D to 1. Set stand to 1. Should store 1. Set clock to 1. Set clock to 0. Set D to 0. Okay, 0. Set clock to 1. Okay, expected value should be 0. It should be 1, but it was 0. So what is the problem here? Problem here is that, when a clock is 0, we should output not the current one, the previous value. Interesting. Interesting. So we depend on clock, right? and we depend on the CT flag. So we should convert this delay in such way that the you know the output, this component should not emit a value immediately. It should emit in next phase, in next clock, when clock is 0. When clock 0, it should work. This should work when clock is 0. What about if we convert and see this way? Look, if this clock is 0, then get this value, okay? Then pass this value to here. Another one. If clock is 0, in that case, get this D and pass this D. Let's check this one, okay? Look to this guy, okay? You can see it, right? So, set D to 1, okay. Set ST to 1, okay, 1. Set clock to 1. Output is not changed. My output is 1, still 1. Anyway, set clock to 0. The stored 1 should be now output. Yes, 1 is output. D is 0. Should store a 0. Yes. Set clock 1. Keys for 0. Maybe this works. Let's check it. We have a very good testing here. Like this is our benefit, our one good benefit. Check solution. Wrong? Check solution. Where? Set D to 1. Set ST to 1. Should store a 1. Should store a 1 but not emit a 1. That's the problem. Then we can use, maybe we can use just and this one and this one, then use this one. Okay, set clock to 1. Set clock to 0. No. When I set clock to 0, the output should anyway go. Okay, it says set t to 1, sets st to 1, should store a 1, yes, change to clock 1, output not changed yet. When clock is 1, when it is 1, output not changes. Okay, 0 should store a 0, set clock to 1, okay, here when I set d to 0, we store a 0, that's fine. When I set clock to 1, we have just 0. When clock changes to 1, sender and when changes to 1, stores the start really is not yet output. Yep. No, this is, should be there should be something in different way to fix this. Okay. So we have select, right, select. Okay, I don't understand here. If I set d to 0, the output should store 0 value. Yes, we store 0 value. Set clock to 1. So if I set clock to 1, then what? Then we ask from d0 and it is 0, so we just emit nothing, just 0. But it's saying expected output to be 1. Let's ask help. What about if we put two D latch together and we make ST as clock and for second one ST as ST. Let's do it. Let's clear canvas. I take D latch, D value, should we do like this? Or should I assign clock to here? If clock is 1, it should do nothing, right? When clock changes to 1, the stored value is not yet output. When it is 1, the stored value should not be output. Okay, when it is 1 and standard st is 1, the current value of d is stored. Our d is stored when this two guys is 1 1. Look, set d to 1. Okay, we have set it to 1. D change only when d this this d value is stored only when clock and standard is 1 1. In that case, let's use the AND value, guys. This is for sure, right? I don't know, maybe like we should just output from here or from here, I don't know. Let's check one more time. I know it looks a bit complicated, so look, we will find a way. So set d to 1. Okay, I set to 1. Set standard st1 should store now, should store 1. Okay, we are not storing 1, but should store 1. What does it mean? When CL changes to 1, the input flag can change in this stage. What? The input flag can change in this stage. Input flags can change in this stage. Okay, it can change in this stage. Here, if st is 1 when clock changes to 1, the current value of t is stored. I applied this condition. Okay, I applied this condition to here. My screen is clear, right? You can see, I mean, like, you can see, we can easily read it, right? No? Should I make it bigger? Write in comments if there's some kind of discomfort, some kind of problem with Gym. Problem. So here it says that when clock is 0, we can store anything. We can get anything. What if then we can just use OR value and use this guy and this guy? Why? Maybe it's incorrect. Let's see a hint. You need to use 2 latches. Yes, 2 latches. Fine. That was enough. That was enough hint. Clear canvas. Definitely we need to use 2 latches. D comes from here. D comes from here. But the problem is that ST comes from where? Is it here? Here? Look. When a clock is 0, you can change it. when clock is 1, D is stored. Okay, set D to 1, set ST to 1, should store a 1, we have a 1, clock is 1. Okay, here, see, when clock is 1, we should not output. Maybe let's put clock to here. Let's start again. D is 1, ST is 1. Oh. No, we should not do like this. We need to use AND maybe here. Still, again, still. Let's start again. D is 1, ST is 1, clock is 1. Output not changed yet, but we are already outputting. That's problem. Set clock to 0. The stored 1 should now be output. You know, the thing is that we need to use inversion. When it is 1, there should be no output. When it is 0, there should be output. Look. We depend on D, okay, D, ST, set clock to 1. Clock to 0. So start 1 should now be output. I am missing something. I am missing something here. So when D is 0, we store a value of 0, right? Yes. When we set clock as 1, the current value of D is stored. We stored it. The stored value is not yet output. So when we store it, we just output it. But they're saying if you store it, but you should not output it. Make sense? What about another design? You just use select and base it on the clock. If clock is 1, if clock is 0, what was that? If clock is 1, output is not changed. Get from here. Otherwise, get from here. No, we need half. We need half. Second half. One ledge should be written when clock is 1. The next ledge should be written when the first ledge. First ledge when clock was 0. Okay. We have 2 ledge. One ledge should be written when clock is 0. This is written only when the ST is 1, based on the clock. Look, when we have a D1, right? When it is 0, we cannot change the state. And when it is 1, we can change the state. Okay, yes. The next ledge should be written from the first ledge when clock is 0. The next ledge should be written from the first ledge when clock is 0. Clock is 0, it should be written. But even it is 0, it doesn't write. It doesn't write. So we need to use inverse here. What about this value? If you look to here, 0, 1, 0, 0, 1 doesn't matter, 0, 0 doesn't matter, 1, 1 matters, 1, 0 doesn't matter. And okay, we set t to 1. Now we store it. We don't store anything. We don't store anything. Should store 1. We are not storing anything. Set clock to 1. I store a 1 now. Set clock to 1. Output not changed yet. Output not changed yet. Set clock to 0. Output is 1. Check solution. Set D to 0. Set standard to 0. Set clock to 1. Since st0, the stored value should not change but remain 1. Yes. Set clock to 0. Maybe we don't need this inversion. No, we need it. Okay, this is tough question. This is tough question. One ledge should be written when clock is 1. The next ledge should be written from the first ledge when clock is 0. No, 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 no. Guys, this is tough question. This is tough question. But here, when we set clock to 0, this ledge should be written from the first ledge. The value of from here should be written to here. I need inversion in that case, right? That makes sense. To use two ledges. Yes, fine. Fine. Our problem is that when we set clock to 0, output should not change. So we need to trigger something more, something else. Well, D1, S1 should store. We are not storing anything. When I set clock to 1, I store something. When I make it 0, it outputs 1. Right. When I set D to 0, output should be D ledge should be 0, no? No, I said 0, it's not working right. Set standard to 0. Nothing changed. Set clock to 1. Ah, okay, here we have a problem. See? See where we have a problem. When clock is 1, the stored value should not change but remain. Look, when clock is 1, we should ask from ST, from these guys. Okay? When clock is 0, What when the clock is 0? Why something wrong? So clock is 1. We need to check the ST and D values. Okay, makes sense. When clock is 0, still use them? So I don't need this guy. Okay, well, let's start from first step. We have a problem in seventh step. So here D is 1, nothing. We store a 1, okay? Now second is completely 100% absolutely satisfied. Clock to 1. No, why we are outputting? No. No, guys. D is 1. SD is 1. Clock is 1. No, we make a mistake. Look. 1, 1. And it starts to work. No, we should only emit when this is 0, right? Clock ticks, clock cycle completes, output should be 1, clock to 0, output is 1, yep. T is 0, SD is 0, 1, 0. Check result. No! Okay guys, I need the help. Flip-flop component that store a bit when clock signal is 1. What? When stores and when clock is 1? Stupid. Okay, hello, Kartsing and Chanuka Pihisara. Mm. I'm definitely making some kind of stupid mistake here, guys. Well, I know a hint. Core idea. Core idea is that we have a two latches, right? And they're interconnected with each other, and we have a condition. This condition is not clear. These conditions are not clear. Can you see my terminal? Okay, good. So it says that we always depend on the clock. First thing is that depends on the clock. What does it mean? It means that we need to check about, we should always check the clock rate, clock value. If clock is 0, emit a stored value. No, it's fine. If clock is 1, it means we can write to the memory, okay? Okay, clock can be in two ways, in two values. It can be either 0 or 1, right? So when 0, emit the memory, emit the value in the memory, okay? Strictly. If it is 1, no emission, but store the value, okay? Based on the STND. I think our problem is here, no emission, okay? We should emit the previous thing. So when the clock is 0, emit. When the clock is 1, you can write here. But when clock is 0, this path is wrong. Because now when I make it 0, it writes this 0 to here. No, no, no. If it is clock is 0, emit what is stored here. Look. Now we store this one, right? When I have 1. 1 means okay, you can store, okay. Our one condition is working fine. If I set clock to 0, what should it do? Okay, when I set clock to 0, this output should, one output should go, okay? Okay, one is going, but when I set clock again to 1, it's still emitting, right? And see now I make this change, have a 0 here, right? When I finish the clock, this 0 goes here. But actually it should not go there. Output should stay 1. That's the problem. maybe we should do something like this here. I know my problem is here. Oh, fix it. This uses fewest possible components, but it's possible to solve with lower total of NAND gates. Guys, congratulations, we fix it. We fix this problem, we fix it. Okay, good. So it turns out that we are wrong because D should not depend on this end condition. D should directly depend on D value. That was our problem. And we had this clear condition when ST is 1 and clock is 1, so we can convert this condition as this end. Fix this D latch and another D latch. Good. Let's go. Let's go to the next one. Register. In memory, no. In processor, we have a register. We have instructions. Yeah, we have set of instructions and we have registers inside the processor. In every processor, almost. It doesn't matter if either it is CPU, GPU, or another special chip. All of them have a register. Okay, it's 7 a.m. so I'm a bit sleepy, guys. Sorry. So you can now store a single bit of data. In this mission, you have to combine two data flip-flops, DFFS, to store and retrieve 2 bits of data in one operation. We need to combine 2 data flops to store and retrieve 2 bits of data in one operation. Ultimately, we want to store and retrieve 16-bit word at a time, but if you figure out how to store 2 bits, storing larger sets is trivial. Trivial stands for it's easy, it's straightforward. Okay. We have DFF component. Except 2 bits. D1 and D0 are stored and emit instead of 1. Okay, this is 2 bit, okay? Clock is here. This guy is here. 4D. What we can do? Let's think. The simple thing which comes to my mind is that what if we take D1, D0 from here and we take for this D from D1 and connect like this and give this D0 to D0, D1 to D1. What is the problem with this guy, with this thing? I don't see a big problem here. Because are we losing any information in this operation? I think no. No, maybe we are losing. Maybe we are losing operation. How this DFF works? It was based on the clock. And when clock is 0, it starts working. Let's check the solution. Okay, we fix it. Good. So this is the register. Okay. It turns out register works in the next clock, right? Clock time. Usually, like why we use a clock, Let's say I have this chip. Can you see it? Let's say I have this chip, and it has also a processor, and the processor here is this guy, this black rectangle one is our processor. Processor name I don't remember exactly, but it is not that strong. It has only one core. In modern computers we have 4 cores. In Intel computers usually we have 4 cores. Core stands for that independent operation inside the processor. But this guy has only one core, and it has very small cache memory. It also has a register. It has all these components, but it is not that strong because it has only one core. And there are other problems, but overall, this guy also used this register, and we created by ourselves this register thing, so that it also here, it gives new power, big power. Okay, so register is like that, like we have an instruction in machine code, like, okay, get this value from the RAM or from the memory, from the disk, and write a value to the register. This is one instruction, and it writes to the register, and when it writes to register, and when the clock ticks one full operation, in that case the register is written. You can use a register. That's the logic of register. Cool. When we are doing the operation like a plus b equal to c, like 2 plus 3 equal to 5, we do like in following, like first instruction for this processor is that get a 2 value and store in register 0. Second instruction, take the value 3 and register this to the register 1. So now we have 2 registers and we have 2 values written to the registers. And the third instruction, maybe this is one approach, is take register 0 and register 1 and do arithmetic logic and write it to the register 3 or update it to register 0 and then return this 0. This is how the processor works. Let's go to the next operation. Okay, counter. A counter component increments a 16-bit number. The next task is to build a counter which increments a number at each clock cycle. Oh, increment a number. Counters drive the execution of instructions. Interesting. This is much simpler, I think. So we have a register. We can write the x, but it depends on the st, and it depends on the clock. But what's the problem? Problem is that if st is 1, then the input value x is used as a new counter value. Okay. If st is 1, then x is used. Okay. When st is 0, clock is 0, set next to output +1. Okay, we need to satisfy this condition, guys. Okay, we have 4 viewers, 4 real-time viewers, guys. Congratulations. So here, when we have a 0, 0, we need to use increment. We get from here, and we need to write it to here. Okay, makes sense. When st is 1 and clock is 0, use this x. Okay, we need to use, maybe we can use this one, select. Select when. Select only when based on this guy. And if st is 1, use this x. When it is 0, use this increment. Maybe correct, maybe no. Let's check. Okay, we have a problem. That's fine. It's completely fine. The current diagram does not comply with the specifications. The specification. These verification steps were performed. Set st to 1. Okay. X to 7. And clock to 0. Okay. This should set in to 0. Why second is empty? Change clock to 0. Okay. Should set out to in. Output should be out. Set clock to 0. Set clock to 0, 1, 0. Guys, see, here is dependency. We are not satisfying this guy because I said it is to 1. This is also 1, and this is also 1. No. This should stay always 1. How can I do it? Okay, fine. 8, 9, okay. Now it works. Check solution. Yes, now we have a, now we satisfied two conditions. Now we have a working code. Next level. Okay, RAM is the last one. Build a memory unit with two 16-bit registers. Okay. I need to use a register. I need to use 16-bit registers, and I need to use two of them, which is addressable and readable using 1-bit address. Oh, okay, we write to the register based on the 1-bit address. Anyway, input AD address indicates which storage unit we are accessing. ST store indicates if we want to write to the unit. 1 value X is stored in the unit. If 0, then X is ignored. X data is 16-bit value. Clock synchronize state changes. X is stored when clock changes from 0 to 1, but emitted only when clock changes from 1 to 0. This condition is applied to our memory before. We did it for here. So that's not big problem. You can now store 16-bit word in a register. We can get more memory just by stacking those registers. But since the processor operates in a word at a time, we need a way to select and change individual words in the larger bank of memory. We use memory addresses for this. We assign each word in memory a number, so we can fetch or override a word by using this number. In this mission, you have to use two registers and address them using a single bit. Okay, we have just 0 and 1, and we need to address, and we need to use two registers. I don't know, like, I know for sure that clock should be clock. Clock should stay, okay. And then X just X. Maybe no, maybe no, maybe yes. Okay, I have a value, let's say this value, right? And I store it to register. And this value is registered here and here. And it says, and it turns out we have an address. Address is used to give, to able to write or overwrite, right? AD indicates which storage unit we are accessing. Oh, okay. It means we can do like this, like if add is 0, use this guy. If address is 1, use this guy. Means like address 1, okay. Everything from here goes to here. Address 0, go to here. Then we use select based on address. If address is 1, go here. If address is 0, go here. And standard is standard. Standard is standard. Output from here. Let's check solution. Oh, wrong. Why wrong? Set address to 1. Standard is 1. Decimal 42. Okay. Should store value to address 1. Aha. You see? It should store a value in address 1. Here it's not writing only to one address, it's writing to both of addresses. it should write only to one address. See? And address is what? Address is, we use address to write or overwrite. Overwrite or write what? A given value. Mm-hmm. Mm-hmm. Instead of this select guy, maybe this is fine. We need more, I think. We use a switch. What is switch? Switch is based on S. We can switch between 1 or 0 based on the S flag. So S flag is our address. D is our X value. If address is 1, we pass it to the here. If address 0, we pass it here. No? What is the input of D? Oh, D is binary. It's not 16 bits. It's binary. Actually, I don't need this guy. Our problem is that we should not write directly X. Our problem is that, you see, we need to write to either this guy or to this guy based on the address. Okay. What we can use? And select. I can use select. If it is 1, I can use 2 select. If it is 1, take it, okay? If it is 0, take from here. Otherwise it is 0. Maybe this maybe it also doesn't work because we override as 0. But ideally we should not override. No, this is wrong, guys. This is wrong. Our X doesn't matter because what writes to the register? This ST writes to the register, right? ST is what? Binary. Then we can use D as ST, address as S. Maybe this is true. Maybe no. See? Okay. We need to use switch. Let's check solution. Okay, level is not correct. Okay, fine. Address is 1, ST is 1, and X is 42. Should store the value 42 at address 1. At address 1, we should store a value. We are not storing anything. Only when clock ticks we store a value. We should change the order. Check solution. We make a mistake here because we should connect this one to here, but we did vice versa. Guys, congratulations. Guys, congratulations. We finished this round. So to sum up, what is RAM? RAM is a collection of registers. That is the thing. Guys, we should feel the processor, okay? We should appreciate the processor. Only in that case we can, truly understand, truly be developer, truly feel this power, okay? So here we have a RAM, okay? We have disk, it is also memory. We have DRAM or RAM, it is also memory. And we have a cache inside the processor. Is cache a memory? Cache store a value, it is also memory in that case. And RAM is just collection of registers. And in different processors we have different number of registers. Okay. And we have address. What does address do? If we have address, if we have only 2 registers, we need just to have a binary address, 0 or 1. Address 0, go to address 0. Address 1, go to address 1. Okay, my chair is noisy. Okay, let's go to next level, last level, the most difficult, most interesting level. Okay, that is a processor, combined memory, LU, instruction control, selector, control unit, computer, input and output. Okay, memory is a processor, consists of 2 16-bit registers called A and D and a RAM unit. We have a RAM which is 16-bit register, but we have another registers and a RAM. A star flags and the X input is used to update 1 or more of the registers. What was the clock? Clock is ticking, right? Have I built a clock? Clock. Do I have a clock? No, I don't have a clock. Have I built a clock? No. I don't remember. Selector, counter, register, clock. It says that we have a RAM inside of this chip, and we also have a registers which are outside of the RAM, which works independently from the RAM. Okay guys, it is 7:26 a.m. Thank you very much for the stream. It is 1 hour and 24 minutes already. Let's see you tomorrow morning, inshallah. So because now I need to go to work, I need to prepare my breakfast and etc. So thank you very much for watching, first of all. And another thing is, congratulations that you are watching and you are interested in solving these interesting, very low level problems in computer science. I can say it's electric engineering almost, but you don't need to be you don't need to have a special education to fix these things, to understand these things. And thanks for your patience. Be patient and be thankful. Have a good, productive day. Push your limits today. Be really positive to everyone. Try to greet everyone. Give some gifts. Be happy and don't hold any negative. Stay positive throughout the day and see you tomorrow. Bye bye guys.